we started discussion for synthesis of organic compounds. So far, we have discussed criteria for ideal synthesis, and then we have discussed principles of green chemistry. In the yesterday's session, we discussed conversion of a reaction, what is percentage conversion, then yield of a reaction, what is theoretical yield, practical yield, and percentage yield. We also work out the formulas to calculate theoretical yield, percentage yield, and percentage conversion. Here, in today's session, we are going to discuss one important concept which usually come across while we design organic synthesis. A reaction in which reactant have more than one functional group or more than one reacting site can give other products than the desired product. To achieve the selectivity in that particular product formation is studied the concept of selectivity, and that concept of selectivity we are going to discuss in today's session. So let's start. Concept of selectivity. What is selectivity and why it is important to measure the selectivity? So selectivity is summarized in one sentence. It is measure of efficiency of a reaction. What we understand by efficiency of a reaction? To understand it better, if I formulate the selectivity, if I write a formula for selectivity in a reaction, then it will be selectivity is the ratio of desired product form to desired product expected. So here we understand what we mean by measure of efficiency of a reaction. A reaction is expected to give 100% desired product, but in practice, only 80% of the desired product is formed and 20% will be the byproduct or side product of the reaction. Then the selectivity will be 80 divided by 100, that will be 80%. So we always measure the selectivity in terms of the desired product, and that translate into the efficiency of the reaction. When we discuss selectivity, reactant can have different functional groups which may undergo reaction under similar reaction condition, or in other words, we can say a reactant can have more than one functional group which react under the reaction condition. In other case, a reactant can have more than one site at which reaction is possible. So selectivity is classified according to the functional group which is undergoing reaction, site in a reactant molecule that undergoes reaction, or the stereochemistry which we expect or which we want to achieve in the product in a reaction. So there are three types of selectivity, namely chemoselectivity, regioselectivity, and stereoselectivity. For today's discussion, we'll be discussing the two types, chemoselectivity and regioselectivity. So let's start with the first type of selectivity, chemoselectivity. What is chemoselectivity and how it is defined? In the reactant, a particular functional group reacts in preference over other functional groups present. So chemoselectivity is the question refer to which functional group react. So in short, one can say when we ask the question which functional group, then that is the problem of chemoselectivity. Say in a reactant, if we have more than one functional group, or if we have two similar functional groups, then only one of those functional group will undergo reaction and the other functional group remain unaffected. So we can say in chemoselectivity, one functional group reacts keeping other functional group intact in a reactant under the reaction condition. So this will be better understood with an example. Consider the reduction of metadinitrobenzene. In this compound, we have two nitro groups, two nitro functionalities. When we try to reduce the metadinitrobenzene using sodium hydrogen sulfide, only one nitro group get reduced and the product form is meta-nitroaniline. So here it can be clearly seen that one of the nitro is selectively reduced to amino group. So sodium hydrogen sulfide is selectively reducing metadinitrobenzene to meta-nitroaniline. This is chemoselectivity. Both the groups present in the reactant are nitro. So they can be reduced. But when we choose a reagent which is selective in nature, like sodium hydrogen sulfide in this case, that reduces only one nitro group. If we use the hydride reducing agent like lithium aluminum hydride, then no chemoselectivity is observed. Both the nitro groups in the metadinitrobenzene gets reduced to amino group and the product form is metaphenylenediamine. This is not a chemoselective reaction because both the nitro groups get reduced. So LAH being a strong reducing agent reduces both the nitro groups in the metadinitrobenzene. Here, when we choose sodium hydrogen sulfide, that selectively reduce only one nitro group and we achieve the desired chemoselectivity. Let's discuss few more examples for chemoselectivity. Consider a beta keto carboxylic acid. This beta keto carboxylic acid, when treated with sodium borohydride and ethanol is used as a solvent, the reaction is carried out at ambient reaction condition. Out of the two carbonyl groups, here in this structure you can see one is the ketone carbonyl group which is blue colored and Another is the carboxylic acid carbonyl group, which is red in color. So these two carbonyl groups are actually different. One is ketone carbonyl group and another is carboxylic acid carbonyl group. When we use sodium borohydride as a reducing agent, it has been observed that only the ketone carbonyl group get reduced to hydroxyl group. The product form is beta hydroxy carboxylic acid here. So a chemoselectivity in which only ketone carbonyl group get reduced, keeping the carboxylic acid carbonyl group intact. In another example, when we have two different functional groups, carbon-carbon double bond and a carbonyl group, both can undergo reduction reaction. If we use lithium aluminum hydride as a reducing agent, then this acrolein, which consists of a carbon-carbon double bond, also a aldehyde carbonyl group, gives only the allyl alcohol as the product. So LAH selectively reduces aldehyde carbonyl group in acrolein. This is because LAH is capable of reducing polar functional group. Here carbonyl group is polar in nature. There is a difference between electronegativity of carbon and oxygen. So carbonyl group is polar in nature. Carbon and oxygen having different electronegativity. But when we consider carbon-carbon double bond, this is non-polar functional group. Both the carbons are having same electronegativity, and LAH, lithium aluminum hydride, cannot reduce non-polar functional groups. So this is again a chemoselectivity reaction where the aldehyde carbonyl reduced to primary alcohol in presence of carbon-carbon double bond. ओके, समजला इथे सर्वांना chemoselectivity? हॅलो
सर रिपीट कर एकदा.
परत सांगा सर.
ओके, गोइंग बॅक. सुरुवातीला डेफिनेशन लक्षात घ्या. chemoselectivity डेफिनेशन काय सांगते की जर रिएक्टंट मध्ये एकापेक्षा जास्त फंक्शनल ग्रुप असतील, आता हे फंक्शनल ग्रुप काय असतात की ते रिएक्शन कंडिशन मध्ये रिएक्ट होऊ शकतात. ओके, सिंपल एक्झाम्पल आपण घेतलं मेटाडायनायट्रोबेन्झीन, याच्यामध्ये दोन नायट्रो ग्रुप आहेत. आता दोन्ही नायट्रो ग्रुप मध्ये आपण डिफरन्शिएट करू शकत नाही, पण ज्यावेळी रिएजंट सिलेक्ट केला जातो सोडियम हायड्रोजन सल्फाइड, त्यावेळी काय होतं की या दोन नायट्रो ग्रुप पैकी फक्त एका नायट्रो ग्रुपच रिडक्शन होतं. थेरॉटिकली आपण काय म्हणू शकतो की दोन्ही नायट्रो ग्रुप आहेत, दोन्ही नायट्रो ग्रुपचं रिडक्शन व्हायला पाहिजे. ओके, आणि आपल्याला जो प्रॉडक्ट मिळणार आहे त्यामध्ये दोन्ही नायट्रो ग्रुपचं NH2 असं रिडक्शन व्हायला पाहिजे अमीन मध्ये. पण रिएजंट जो सिलेक्ट केलाय त्याची सिलेक्टिव्हिटी किंवा त्याची आपण म्हणू शकतो त्याची कॅरेक्टरिस्टिक काय आहे की तो फक्त एकाच नायट्रो ग्रुपला रिड्यूस करेल. म्हणजे इथे सिलेक्टिव्हिटी आहे. दोन फंक्शनल ग्रुप पैकी फक्त एकच फंक्शनल ग्रुपचं रिडक्शन होतं. ओके, सुरुवातीला सिलेक्टिव्हिटीची कन्सेप्ट समजून घ्या. सिलेक्टिव्हिटी म्हणजे काय? ठीक आहे, IPL तुम्ही सगळे पाहत असाल. क्रिकेट मध्ये मला वाटतं बहुतेकांना तुमच्यापैकी इंटरेस्ट असेल. IPL मध्ये किती प्लेयर्स असतात एका टीम मध्ये? ते ऍक्च्युअल मॅच मध्ये पार्टिसिपेट करतात? पटपट उत्तर द्या. किती प्लेयर्स असतात क्रिकेट टीम मध्ये एका?
11.
बोला पटपट. रिपीट करायचं तर तुम्ही बोललं पाहिजे, मला काय समजणार आहे?
11.
11.
क्रिकेट पाहता की नाही पाहत?
नाही.
ओके. 11 प्लेयर्स असतात. पण तिथे तुम्हाला समजत असेल की ज्यावेळेस टीम सिलेक्शन होतं ते टॉसच्या वेळेस सांगतात टीम सिलेक्शन. तुम्ही ते ड्रीम 11 त्यानंतर अजून बऱ्याचशा साईट आहेत, तुम्ही पण काही ते टीम वगैरे सिलेक्ट करत असता. तर तिथे किती असतात तुमच्याकडे? 15 प्लेयर्स असतात किंवा मॅनेजमेंट जे टीम मॅनेजमेंट असतं त्यांच्याकडे 15 प्लेयर्स असतात. 15 पैकी त्यांना काय करायचं असतं? एक 11 प्लेयरची टीम ही त्या मॅच मध्ये खेळवायची असते. तर 15 पैकी 11 सिलेक्ट करायचे, म्हणजे तिथे सिलेक्शन आहे. इथे पण तसंच आहे. इथे काय आहे? 2 फंक्शनल ग्रुप आहेत किंवा आपण जनरल म्हणून एकापेक्षा जास्त फंक्शनल ग्रुप आहेत. ओके, रिॲक्शन होणार आहे, पण ही रिॲक्शन होताना या दोन्ही पैकी किंवा एकापेक्षा जास्त फंक्शनल ग्रुप असतात त्यापैकी फक्त जे सिलेक्टेड असेल त्याचीच रिॲक्शन होईल, बाकीचे रिॲक्ट होणार नाही. म्हणजे याला म्हणतात प्रॉब्लेम ऑफ विच. म्हणजे जर एखादा क्वेश्चन मी तुम्हाला विचारला विच फंक्शनल ग्रुप react, which that is chemoselectivity. Understand? आता सेम रिॲक्शन जर मी LH वापरून केली, LH हा स्ट्रॉंग रिड्युसिंग एजंट आहे, इथे काही सिलेक्टिव्हिटी नाहीये. इथे काय होतं की सगळेच्या सगळे फंक्शनल ग्रुप म्हणजे हे दोन्ही नायट्रो फंक्शनल ग्रुप आहेत ते रिड्यूस होतात आणि दोन्ही पासून आपल्याला अमिनो ग्रुप मिळतो. म्हणजे आता क्रिकेटचं उदाहरण घ्यायचं तर 15 प्लेयर जे आहेत, तर मी म्हणालो की प्रॅक्टिस सेशन आहे. प्रॅक्टिस सेशन मध्ये सगळे 15 जण पार्टिसिपेट होऊ शकतात. ते काही जे 11 खेळणार आहेत तेच प्रॅक्टिस करतात असं काही नाही, प्रॅक्टिस सर्वांनाच करावी लागते. ओके, तर तिथे काही सिलेक्टिव्हिटी नाहीये. देर इज नो क्वेश्चन ऑफ सिलेक्टिव्हिटी. सो हिअर ऑल्सो यू कॅन compare. If I use strong reducing condition, it is strong reducing condition आहे. LAH is a strong reducing agent. It reduces both the nitro group and the product form is metaphenylene diamine. Okay, इथे selectivity नाही. Where is the selectivity? When out of the 2 nitro, only one group get reduced to amino. Okay. Similarly, आपण 2 एक्झाम्पल स्टडी केले. पहिल्या एक्झाम्पल मध्ये काय आहे की 2 कार्बोनिल फंक्शनॅलिटीज आहेत. एक ब्ल्यू कलरची जी कार्बोनिल फंक्शनॅलिटी आहे ती तुमची कीटोनची आहे आणि दुसरी जी कार्बोनिल फंक्शनॅलिटी आहे ती कार्बोक्सिलिक ऍसिडचा पार्ट आहे. सोडियम बोरोहायड्राइड काय करतो? फक्त कीटोनची जी कार्बोनिल फंक्शनॅलिटी आहे त्याचं रिडक्शन करतो. कीटोनचं रिडक्शन झालं सेकंडरी अल्कोहोल तुम्हाला मिळेल. ओके, सो यू कॅन सी ओनली दी कार्बोनिल ग्रुप विच इज ब्ल्यू कलर्ड इज गेटिंग रिड्यूस टू हायड्रॉक्सिल ग्रुप. कार्बोक्सिलिक ऍसिडचा कार्बोनिल ग्रुप हा इंटॅक्ट राहतो, अनअफेक्टेड राहतो. नेक्स्ट एक्झाम्पल मध्ये आपण काय डिस्कस केलं? आता इथे कार्बोनिल होते, पण मी समजा दुसरे फंक्शनल ग्रुप घेतला. एक कार्बोनिल आहे आणि दुसरा अल्कीन आहे किंवा कार्बन कार्बन डबल बॉन्ड आहे. आपण कार्बोनिल ग्रुपचं पण रिडक्शन करू शकतो, आपण कार्बन कार्बन डबल बॉन्डचं पण रिडक्शन करू शकतो. रिएजंट जर मी सिलेक्ट केला LAH, तर LAH काय करेल? LAH हा असा रिएजंट आहे की जो फक्त पोलर फंक्शनल ग्रुप जे आहेत, पोलर फंक्शनल ग्रुप म्हणजे नायट्रो ग्रुप असेल, कार्बोनिल ग्रुप असेल किंवा नायट्राइल ग्रुप असेल किंवा कार्बोक्सिलिक ऍसिड ग्रुप असेल, अशाच फंक्शनल ग्रुपचं रिडक्शन करतो. नॉन पोलर फंक्शनल ग्रुप म्हणजे कार्बन कार्बन डबल बॉन्ड, कार्बन कार्बन ट्रिपल बॉन्ड यांचं रिडक्शन LH करत नाही किंवा LH मुळे हे ग्रुप रिड्यूस होत नाही. मग आपल्या रिॲक्टंट मध्ये इथे जे एक्झाम्पल दिलंय ऍक्रोलिन नाव आहे त्याचं, यामध्ये जो कार्बन कार्बन डबल बॉन्ड आहे तो रिड्यूस नाही होणार. तो अल्डिहाइडचा कार्बोनिल ग्रुप आहे त्याचं प्रायमरी अल्कोहोल मध्ये रिडक्शन होईल. सो हिअर वी कॅन से विच फंक्शनल ग्रुप अंडरगो रिडक्शन? The aldehyde carbonyl undergo reduction and carbon carbon double bond remains unaffected. Okay, this is chemoselectivity. समजले? Hello?
Yes, sir.
Okay, read it.
Yes, sir.
You will understand. Okay, remember one key word. Which functional group? Okay, whenever there is a question, starts with which. Okay, कोणताही प्रश्न जो प्रश्न which ने start होईल, okay, तो असेल तुमचा chemo selectivity. Okay. Next type of selectivity we are going to discuss is regioselectivity. What is regioselectivity? In the reactant, a particular site undergoes reaction in preference to similar other sites present. Here, when we ask the question, here the reaction takes place. That poses the problem of regioselectivity. So in a reactant, if there are more than one sites which are capable of undergoing reaction, and out of those, only one site undergoes reaction over the other similar sites, is the regioselectivity in the reaction. Remember, the key word here is here. Here the reaction takes place, and that indicates the regioselectivity in the organic synthesis. Let's discuss with an example. You already have studied addition of halo acids to unsymmetrical alkene. The addition reaction proceeds with Markovnikov's rule. And when it follows Markovnikov's rule, a major product where the more stable carbocation is formed is like this. Here, the minor product is also possible, in which the hydrogen is attached to the center carbon and halogen to the terminal carbon, and that results in the formation of minor product. So this particular addition of halo acid to unsymmetrical alkene proceeds with major product form as per the Markovnikov's rule. Here, the minor product is also possible. To understand this better, one can see when the addition of halo acid takes place, there are two sites or two carbon atoms to which the hydrogen and halogen can get attached or can be added. Now, according to Markovnikov's rule, halogen prefers to attach to this carbon because it gives the more stable carbocation, and hydrogen will attach to this terminal carbon, and that gives the formation of the major product. In this reaction, minor product is also possible, where the hydrogen can attach to this carbon and halogen can add to this terminal carbon, and that results in the formation of this minor product. So here we have two sites for addition of halogen. According to Markovnikov's rule, the addition of X results in the formation of more stable carbocation gives the major product, while the addition of X according to anti-Markovnikov's addition gives formation of this minor product. Here, the efficiency of a reaction is lost. We said selectivity is a measure of efficiency of a reaction. So here, because of the formation of minor product, okay, the percentage of major product form will be reduced. In this particular reaction, the ratio ranges from 80-20 to 95 to 5%. So this is regioselectivity in a reaction. Let's see few more examples for regioselectivity. Aromatic electrophilic substitution reaction, say nitration, are extensively studied. When a benzene ring is activated by attaching electron donating group, then the nitration results in the formation of two regioisomers, para-isomer and ortho-isomer. But when the reaction of nitration is carried out where benzene ring is attached to electron withdrawing group, it gives meta substituted product. So here we can see the sites of reaction or the substitution where the nitration takes place. In electron donating groups, the ortho and para position are preferred. So this is the selectivity. Here in this particular reactant, we have ortho position, we have meta position, we have para position available for nitration. But selectively, para-nitro and ortho-nitro products are formed. Out of these two, para-nitro and ortho-nitro, okay, para will be formed in more percentage. So para will be the major product and ortho will be the minor product. In another example, when benzene ring is attached to electron withdrawing group, in that case, nitration results in the formation of meta-nitro substituted product. Here, we can say in electron withdrawing group attached to benzene ring, there are three sites available for substitution: ortho, meta, and para. But because of the directing effect of this electron withdrawing group, the product form in which the nitro group is attached to meta position. So we get meta substituted nitro product in the aromatic electrophilic substitution reaction. So here the regioselectivity is directed by electron withdrawing group. The above example, electron donating groups, which directed the substitution at para and ortho position because of the plus I and plus R effect. So in this example, where we have ortho, meta, and para, these are the three sites available for the reaction. Out of the three sites available, the reaction occurs at para and ortho positions only. So this is regioselectivity. Electron donating groups direct the incoming electrophile to ortho para positions. So these are the two types of selectivity we have discussed in this session: chemoselectivity and regioselectivity. Stereoselectivity is the part for your syllabus we'll be discussing in the